So let's go ahead and finish up chapter 4. That look about right? We're kind of at the tail end here. We're talking about cytoskeleton. And so we just got done talking about the 3 major fibers of the cytoskeleton. We talked a little bit about the actin filament, and I like this image because what this image does for us is it kind of gives you a really good idea. And this is actually a pretty rare image, believe it or not. I don't see really something like this in most textbooks. And so this is the one nice thing about the McGraw-Hill. They do have some nice images that kind of pulls everything together, but it basically gives you an idea of what all the cytoskeletal fibers look like in context. So kind of what they look like and their role in the cell. So you can take a look at the actin filament where you can see basically you got these 2 chains of actin twisted together. And they're little, right? So this is called a microfilament. This is the smaller of the 3. So it's only 7 nanometers in diameter. So it's pretty tiny. And you can kind of see this sort of throughout. So here you can kind of see 3 little fibers of actin filaments that kind of basically goes throughout the cell itself. Now, also then you're going to see the microtubules. Now the microtubules are the ones that we study the most, right? So these are the ones that are the hottest ones to study. Everybody likes to study these ones. But these are also the biggest. So you're coming in at 25 nanometers, and you can see that basically these are just stacked tubulins, right? So you have 2 different types of tubulins, a dimer, a heterodimer. That basically means you have 2 different types of subunits, an alpha tubulin and a beta tubulin that basically comes together as a team. And then you stack this dyad, if you will, this doublet, you stack that together. And that's what the light and the green is. The light and the green basically represents the 2 different types of tubulin that you're stacking in order to make this kind of long cylinder. And it's kind of big, right? So you can kind of see these are microtubules all kind of throughout here. And the reason why these are the hot topics for study is because this is kind of what cellular motion and locomotion is centered around, right? So when we're trying to figure out how do vesicles move around in the cell, things like that, it brings us to microtubules. And we'll talk a little bit more about that here in just a second. But the important thing to understand about microtubules is that they have a sense of polarity to them. That is to say, they have what's called a plus end, which is the growing end. And then they have a negative end, which is kind of like, I guess, what the degrowing end. I don't know what the opposite of growing is, so shrinking end, I guess. Right. So if you, for instance, wanted to expand out this microtubule, all you have to simply do is just stack more tubulin dimers on the end of the plus end. So this is the direction it grows. So if you wanted to grow this out longer, you basically grow it in this direction by simply just stacking tubulin on the end of it. And not only that, but if you want to deconstruct it, all you have to do is just unstack the tubulin. It's very simple, very straightforward. And as a result, because you have this growing end, this plus end, the growing end, basically what that means is you can extend a microtubule out and you can retract it, and extend it, and retract it, and extend it, and retract it. So it's very dynamic. Both of these guys are very dynamic. They're designed to sort of expand and contract and grow and shrink. Now, the one that's not dynamic is the intermediate filaments, right? These are the static ones. And they're made of different types of proteins, but they're all fibrous in nature, right? So for instance, we took a look at the nuclear lamina. So the nuclear lamina is a type of intermediate filament that's made of laminin, right? So that's a good example of the role of an intermediate filament in the cell itself, right? So the intermediate filament oftentimes will represent kind of a scaffold, sort of a framework around which basically you build the cell. And it is also a fiber, but it's kind of a cable of cables. So like if you take a look at this particular large filament, it's basically made of smaller filaments. And if you take a look at a cross-section of those filaments, it's actually made of even smaller fibrous proteins. So if you've ever seen a suspension bridge, like the cable, like the Golden Gate, for instance, or the Bay Bridge, or the Brooklyn Bridge, if you cut that suspension cable in half that holds the bridge up, what you'll notice is that suspension cable is actually a cable of cables of cables of cables. So they're like nested cables. So if you take a look at the giant cable that holds the bridge up, it's actually composed of a bunch of smaller cables, which are themselves composed of smaller cables, which are composed of even smaller cables, right? So you kind of have this sort of nested cabling system, and that's kind of what you've got here in intermediate fibers. But the reason why I like this one is in particular for the intermediate fibers, because a lot of times our only introduction to intermediate fibers is the nuclear lamina. And a lot of times we don't really, kind of get an idea of like, oh, wait a minute, what does this look like in the rest of the cell? And this is a really, really good image to show you what the intermediate filaments are doing in the rest of the cell. So you can see here the intermediate filaments, which are basically all these little tan colored ribs, are basically the scaffold for the cell. It's basically scaffolding the kind of a structural framework, if you will, throughout the cell. And it doesn't go anywhere. It just stays put. So it's basically literally just like a frame. It just stays there. And it kind of holds everything up, and it also holds everything in place. So if you notice, you also have points of attachment to your intermediate filaments here and here and here. So where you actually can stick organelles to these intermediate filaments and sort of keep your organelles sort of in place and tethered into a stationary place. And this is a good idea, right? That way you don't have these organelles sort of free floating all over the place. So when you want to do something like the endomembrane system, right, the secretory pathway, when you're trying to move a vesicle, say for instance, from the rough ER to the Golgi, it'd be kind of nice if the Golgi wasn't just floating all over the cell, right, like a moving target. So it's like you're trying to figure out, where are you now, right? How do I get to you? Since the Golgi is actually tethered to the intermediate filaments portion of the cytoskeleton, then you know that your Golgi is always going to be there, so you don't have to worry about it. Okay. And that's the reason why I like this, because it really does show you how everything is tethered to this intermediate filament component of the cytoskeleton. And it's within that context then that the microtubules, for instance, which are also tethered, if you can see here and here, are also tethered to the intermediate filament portion of it. But it's within that framework that these other two can be dynamic. Okay? So you don't just get to grow willy-nilly. You're still kind of tethered to that scaffold, the intermediate filament scaffold. So let's take a look at, and there's, we're going to be talking mostly about microtubules and the functions of microtubules for the rest of this section, because that's just what we like to study and talk about. But we want to take a little bit of look, and there's a bit of a parentheses that I'm going to take a look at here in about a slide or two. But we want to get this conversation started off first of all, right? Because we already talked about it. We already talked about microtubules having a plus end, right? A growing end and a negative end or a minus end. So the question is, if you wanted to say, for instance, grow a microtubule, how do you get it started? Right, that's the hard part. Once it's there, it's easy because you just stack stuff on the plus end, right? But how do you get there in the first place, right? I mean, you got a lot of cell, there's a lot of places just all over the place. So how do you know to start, say, for instance, here as opposed to here? So where do you get this thing started? Well, you have to have some sort of a frame of reference. Right? You can't just basically start making microtubules out of nowhere. It's just like when you're road making, right? I mean, you don't make a road out of thin air. I mean, you usually have a reference point. You start somewhere. I want to start from here to here. You start with a beginning point and a destination, and that's the road connects the two. So the same thing is also true for microtubules. So then how do we go about organizing? How do we go about actually getting this started? Well, what we have is what's called a microtubule organizing center, or a MOC. And that's simply, all this is a nucleation point for microtubule stacking. So that's basically what it is. And so it's simply just the nucleation space. So in animals, there's a specific microtubule organizing center called the centrosome. And what a centrosome basically is a pair of substructures called centrioles. So if you take a look at a centrosome basically looks like this. There's this like little drum of microtubules, and there's actually two of them, and they're actually perpendicular to each other. So this is actually made up of microtubules. So each one of these little drums is a centriole, and both of these guys together is a centrosome. So this represents the microtubule organizing center in animals. So, and that's helpful, but here's the problem. If you take a look at plants, they don't have centrioles. So basically, for a plant, they have an MOC, but it's not a centrosome. They do it some other way. And as a matter of fact, there's some textbooks, I think this has been written out because it's been updated. But there were actually at some points, just even a few years ago, 10 years ago, where a common question in a chapter like this would be like, what is it? What does it do? Right? So what is this organelle? What does it do? And when you came to the centrosome, some of these books would be like, okay, this is a centrosome. What does it do? Unknown function. It's like, no, that's not true. We do know the function of it, but the reason why these books would say unknown function is because there's no centrosome in plants. And so they don't know what does the organization in plants. And so then they would incorrectly say that we don't know what the function of the centrosome is, which is not true. We know exactly what the centrosome's function is. We understand it very clearly in animals. What we don't understand is what the microtubule organizing center is in plants, because they don't have a centrosome. Not that we don't know what a centrosome does. We know what it does, right? It's just that we don't know how plants organize everything, but they do organize everything. They have to. So this is what a centrosome looks like. So you can see this is the individual centriole. So you have two centrioles. So this would represent a centrosome. And when you take a look at this, the structure of this is very important, because what you see is the centriole has basically these microtubule triplets connected to each other. And there's 9 of them. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 around a hollow core. That's important. Remember that structure, because we're gonna see something very similar to that here in a couple of slides. Now, the reason why this is important is because if you have these 2 little microtubule drums, what this basically means is if you want to grow a microtubule out, then all you have to have is a centrosome, an organizing center, and just start stacking tubulin. So if you start stacking tubulin on the ends of these microtubules, you can start to extend microtubules in pretty much any direction that you would like to go. As many as you wish. You don't have to use all 3 of them. But since it's a circular structure, pretty much you can go just about anywhere you want. Same thing's also